An area navigation, or RNAV system, is a method of navigation which permits aircraft operations on any desired track within the coverage of station-referenced navigation signals, or within the limits of a self-contained navigation system, or a combination of these. This is the ICAO Annex 11 definition. So there is no requirement to fly directly over ground-based facilities. A certain standard of accuracy must be met when RNAV is used, and this is called Required Navigational Performance, RNP. If the standard of navigational accuracy is, for example, 1 nautical mile, then this standard has to be met 95% of the flying time in both lateral and longitudinal directions. RNP can be specified for a route, a number of routes, an area, a volume of airspace, or an airspace of defined dimensions. The required accuracy is achieved by using some or all of the following inputs of information: VOR DME, GPS, ILS or MLS, INS or IRS, Air Data Computer, and time. The information is processed within the system to give the most accurate and continuously updated position and the necessary outputs to provide the pilot with information such as course and estimated time of arrival. Traditionally, an aircraft will follow airways, flying from one VOR DME to the next. RNAV allows aircraft to take a more direct flight path appropriate to the route they are flying, thereby improving the operating efficiency and helping in relieving congestion on the overcrowded airway system. Operating efficiency is improved because of less distance travelled, less time taken, less fuel used, and so less cost. RNAV also produces an increased route capacity because of an increased number of routes, a possible reduction in vertical and horizontal separation, greater pilot choice of routes, ATC-prepared RNAV routes and airspaces, the establishment of bypass routes for aircraft flying over high-density terminal areas, the establishment of alternatives or contingency routes on either a planned or ad hoc basis, the establishment of optimum locations for holding patterns, and a reduction in the number of ground facilities. There are two types of RNAV system: basic and precision. Basic RNAV, known as BRNAV, is required to give lateral and longitudinal position accuracy to within 5 nautical miles on 95% of occasions. It is mandatory for all aircraft carrying 30 passengers or more to have BRNAV capability within Eurocontrol airspace. Precision RNAV, PRNAV, must be accurate to within 1 nautical mile on 95% of occasions. PRNAV routes are now being established in terminal airspace. There are 3 levels of RNAV capability. 2D RNAV provides guidance only in the horizontal plane. 3D RNAV adds guidance in the vertical plane, and 4D RNAV adds a timing function. The flight deck of a simple 2D RNAV system includes several components: It has a navigation computer unit into which waypoint data is input, namely a waypoint number, a beacon frequency, bearing, and distance from the beacon to the waypoint. It has a control display unit and an indicator in the form of an HSI. The deviation bar on the HSI will have a full-scale deflection of 5 nautical miles in en route mode, 1 1/4 nautical miles in approach mode, and 10 degrees in VOR DME mode. A simple RNAV system uses rho theta, that is, range and bearing, to define position, which is derived from VOR and DME stations. The pilot defines waypoints along the route to be flown as range and bearing from suitably located VOR DME. Here, we see that a pilot wishes to fly from Southend, Sierra November Delta, to Newcastle, November Echo Whiskey. There are beacons close to his route: Lambourne, Lima Alpha Mike; Daventry, Delta Tango Yankee; and Pole Hill, Papa Oscar Lima. If he were to fly from one beacon to the next, it would not be the shortest route. The RNAV system allows the pilot to create waypoints, called phantom stations, based on range and bearing information from the VOR and DMEs. He then flies a straight line between the waypoints. The first waypoint has a bearing of 067 degrees from the Delta Tango Yankee VOR, so it is on the 067 radial, and it is 42 nautical miles away from the beacon. The pilot selects the waypoints, plots, then measures range and bearing from the VOR DME. Waypoint 2 is created at a bearing of 066 degrees from the Papa Oscar Lima VOR DME, and at a distance of 29 nautical miles. Waypoint 3 is created at a bearing of 218 degrees from the November Echo Whiskey VOR DME, at a distance of 26 nautical miles. The procedure so far has brought the pilot to a point where he can now start his approach to his destination, Newcastle. He selects the locator outer marker as waypoint 4, which is on the November Echo Whiskey 257 radial at 4 nautical miles. This is the starting point of the ILS procedure. He can then select the ILS at Newcastle Airport, which he designates as waypoint 5. Finally, we can see from this table the inputs that would be required for the RNAV route we have just created. How does the RNAV system work? In our example, the aircraft is flying from waypoint 1, defined by Daventry VOR DME as bearing 067 degrees, range 42 nautical miles, to waypoint 2, defined by Pole Hill VOR DME as bearing 066 degrees and range 29 nautical miles. As the aircraft arrives at waypoint 1, Pole Hill is selected. The bearing is measured as 145 degrees and the range as 104 nautical miles. The RNAV now knows its position with relation to Pole Hill, and the pilot has input waypoint 2 with respect to Pole Hill, so the computer can compute the track and distance from waypoint 1 to waypoint 2. Since it has two sides of a triangle, the angles and the orientation of magnetic north. The RNAV now continually computes the aircraft position with respect to pole hill and compares this position with the computed track to determine the cross-track error and the distance to go. Steering demands are fed into the HSI and performed either manually or by the autopilot. Let's look at some limitations associated with a simple 2D system. Because VOR-DME emissions are line of sight, a pilot must be aware of the altitude at which he chooses to fly and must consider the masking effects of any intervening features, such as mountains. VOR beacons have a designated operational coverage, so the waypoints chosen must be within the DOC. The pilot must ensure that the information is correctly entered into the CDU and must then carefully check that it is correct, because the computer cannot recognize or rectify mistakes. DME ranges are slant range and not ground distance, which we call plan range. When the aircraft is a reasonable distance from the beacon, there is no real discrepancy between the two measurements. But when the aircraft is close to a beacon, say 1 nautical mile away, the slant range is effectively the aircraft height, which, for instance, would be 4 nautical miles if the aircraft were flying at 24,000 feet. In the case of 4D RNAV, the equipment is far more sophisticated than 2D RNAV, and usually takes the form of an integrated flight management system, which we will look at in its own lesson. A full FMS will have IRS and possibly GPS as inputs as well. The information is compared with DME and occasionally VOR-DME in order to calculate a most probable position. Wherever possible, the computer would choose 2 DME signals to establish its position, as an exact position is indicated at the point where 2 DME arcs cross-cut. Only if 2 DME stations are not available will the computer use 1 VOR and 1 DME, because a VOR without a DME function is accurate only to within 5 degrees. Consequently, the aircraft's position is less precise. These fixes are not used at ranges above 35 nautical miles. In order to calculate progress, the 4D RNAV computer receives true airspeed from the air data computer and a heading input which enables the calculation of actual wind velocity. The computer is able to perform great circle navigation when receiving VOR-DME stations. However, because the distances between DME stations is unlikely to be more than 300 nautical miles when operating on overland airways, there will be little difference between rumline and great circle distances. If out of range of VOR-DME stations, the system reverts to dead reckoning, or DR mode, where it updates the position by means of IRS and GPS information, if incorporated, or last computed wind, true airspeed, and heading information, if not. Operation in this mode is time-limited. These are the main points to remember. Area navigation is a system of navigation which permits aircraft operation on any desired flight path within the coverage of station-referenced navigation aids, or within the limits of self-contained aids, or any combination of these. It permits direct routings. It reduces flight times and therefore fuel burn. It increases the capacity of airspace. The required navigational performance for basic RNAV is plus or minus 5 nautical miles. For precision RNAV, it is plus or minus 1 nautical mile. There are 3 levels of capability, and an aircraft must have the required level of equipment. 2D is horizontal guidance, using phantom stations created from VOR DME stations. 3D RNAV adds guidance in the vertical plane, and 4D includes a timing function. The HSI displays the range and bearing to the waypoint, not the VOR or DME. The VOR and DME stations chosen should be associated, which means that they are very close to each other. It is essential to measure ranges and bearings accurately. The route and flight level chosen must permit line-of-sight operation with the beacons. The route must be within the DOC of the ground stations. Be aware of the effect of slant range when close to or overhead a beacon. This concludes the RNAV lesson. We'll next go on to FMS, which is the 4D case in more detail.